Sound characteristics and sources. Sound is a longitudinal wave that can travel through any kind of matter, but not through a vacuum. The speed of sound is different in different materials. In general, it is slowest in gases, faster in liquids, and fastest in solids. The speed depends somewhat on temperature, especially for gases. And please click here for a video on how sound waves move in different gases. Many of our problems will involve sounds that we hear in the air. Although the speed of sound in air can vary, we will use 340 meters per second for the speed of sound in air for most problems. Why? Because we don't have a 3 there at the end, so it's a little easier to multiply. Because sound is a wave, we can still solve for the wavelength or the frequency of a sound using velocity is wavelength times frequency. Sound waves are produced by vibrations that have frequencies between 20 and 20,000 hertz. And some definitions here. Pitch, that's how sounds are heard. The pitch is directly proportional to the frequency. Higher musical notes have a higher pitch and higher frequency. The audible range, that's the sound that humans can hear, is about 20 hertz to 20,000 hertz. The upper limit decreases with age. Ultrasound, that's above 20,000 hertz, and then infrasound is below 20 hertz. Let's work a problem. A sound wave has a frequency of 300 hertz in air. What is its wavelength? Here's our givens, here's the frequency, and we weren't given this in the problem, but we talked about that a couple slides ago. We're going to use the velocity of sound as 340 meters per second. We use the speed of sound equation, but we want to find the wavelength, so we go ahead and solve for lambda. And we do that by dividing both sides of the equation by frequency. We put in our givens, and then we get a wavelength of 1.13 meters. And remember, hertz is seconds per inverse, or 1 over seconds, so that cancels out here, and you get meters as your proper unit. An echo off a building is heard 1.5 seconds after the sound is made. How far away is the building? Our givens are 1.5 seconds and the velocity of sound. Now, before we start solving the problem, let's see what we have. Since the echoes bounce off a surface and come back, 1.5 seconds is the time it takes for the sound wave to go to the building and come back. So here's the person and here's the building. Sound wave goes here and bounces back. That means the distance the sound wave travels is twice the distance to the building, which is what we're trying to find. So to calculate the distance to the building, substitute half of the time. So instead of putting in 1.5 seconds, we put in half that, which is 0.75. So here's our velocity equation. We solve for d by multiplying both sides by t, substitute in our givens, and we substitute in half the times. And the distance to the building is 255 meters. A student hears thunder 6 seconds after a lightning strike. How far is the student from where the lightning struck? The givens are right here. And unlike the echo problem, the sound from the thunder is a one-way trip, right? It just comes from the thunder to the listener. So this time, we just use the given value of the time, which is 6 seconds. We have our constant speed equation, solve for d by multiplying both sides by the time, put in our givens, and we get the lightning hit at 2,040 meters. Loudness and intensity, two related things, but a little bit different. The intensity of a wave is the energy transported per unit time, that's power of course, across a unit area and depends on the amplitude of the wave. So the intensity is power over A. The total energy carried by the wave remains relatively constant, so the power remains relatively constant. The surface area of a sphere is 4 pi r squared, a little bit of geometry and algebra there. So the intensity is inversely proportional to the distance from the source. The human ear can detect sounds with an intensity as low as 10 to the minus 12 watts per meter squared and as high as 100 watts per meter squared. Because of the wide range of human sound perception, intensity is typically measured in decibels, and that is called loudness. So we have intensity over here, and then we have the sound level, which is what humans perceive. The decibel scale is based on the minimum threshold of human hearing, 10 to the minus 12 watts per meter squared, and that will be 0 decibels. Every time intensity increases by a power of 10 in watts per meter squared, the value in decibels only increases by the addition of 10. So let's take where you go from the threshold of hearing to a quiet radio. Intensity has increased by 10,000, which is 10 times 10 times 10 times 10, right? 10 to the fourth. The increase in decibel level is only 10 plus 10 plus 10 plus 10. Did I say that 10? Well, anyway, it's 40. So you can see the quiet radio is 40 decibels and the threshold of hearing is 0. So it's a logarithmic scale. An increase in sound level of 3 decibels, which is a doubling in intensity, that's a good rule of thumb, is a very small change in loudness. Humans perceive loudness, not intensity. In open areas, the intensity of sound diminishes with distance. 1 over r squared it's proportional to. However, in enclosed spaces, this is complicated by reflections, and if sound travels through air, the higher frequencies get preferentially absorbed. No, this is not an anatomy class, but the ear is a pretty complex system. Got 3 tiny bones in here, and you have an auditory nerve that goes right to the brain, and various other biological stuff. But once again, here's the key. Loudness is the perception of the intensity of a wave and depends on the physiology of the ear. You can see there's a lot of moving parts in there, and how sensitive it is to vibrations. And this eardrum here, that's one of the reasons that as you get older, you don't hear higher frequencies. What happens is that stiffens over time and it won't vibrate as fast. So that'd be a good test. You can Google that on the web and test what older folks like myself can hear in terms of frequencies versus younger people. So here's a short explanation of the ear. You've got the outer ear, where sound waves travel down the ear canal to the eardrum, which vibrates in response. Then you have the middle ear, which are the little bones there, hammer, anvil, and stirrup, and they transfer vibrations to the inner ear. And then the inner ear, you have the cochlea transforming vibrational energy to electrical energy and sending signals to the brain. And here's a nice video to sum that up. Musical instruments produce sounds in various ways: vibrating strings, vibrating membranes, vibrating metal or wood shapes, vibrating air columns. And you can see the key word there. The vibration may be started by plucking, striking, bowing, or blowing. The vibrations are transmitted to the air and then to our ears. The strings on a guitar can be effectively shortened by fingering, raising the fundamental pitch. So if your left hand, let's say you're righty, if your left hand is way up there and you're plucking down here, you get low notes. When you bring your fingers down here, which Jimi Hendrix used to do a lot, you get the higher notes, the higher pitches. The pitch of a string of a given length can also be altered by using a string of different density. And you can click here for video on guitar string pitch. A piano uses both methods to cover its more than 7-octave range. The lower strings are much longer and much thicker than the higher ones and give you the low notes, and up here the high notes. The strings on stringed instruments produce a fundamental tone or frequency whose wavelength is twice the length of the string. That was shown in the waves unit of this course, the one right before this one. The product of string length and pitch is a constant. So the length increases as you go this way, but the pitch increases this way. You get the higher notes up there. So another video to observe the relationship between wavelength and frequency. The speed of a wave on a string depends on the tension and the linear density of the string. The speed of sound in air is approximately 340 meters per second. We've said that a few times, but just a reminder. As the sound wave changes medium from the instrument string, right? You've got the string vibrating here, and then it starts vibrating the air molecules. the speed and wavelength of this wave that started out on the string will change. But here's the key. The frequency remains constant. Wind instruments create sound through standing waves, and we talked about that in the last unit also, in a column of air. Column of air is going through like that. And here's a video on sound in air columns.